Hi everyone, this is Babaiah, Assistant Professor of ECE Department, MLR IT, Hyderabad. Today I am going to explain the root locus or root loci. What are the basics and also what are the rules for the construction of root locus. All these are we are going to learn from the today's session. In previous session we learn how to solve the special cases of RH criterion method or Routh-Hurwitz criterion method. All are we learned from the previous session. Now coming to the overview of today's session, just observe here the basics of root locus and the importance of root locus. What are the rules for the construction of root locus? What are the rules for the construction of root locus? All these, some of the rules in this class I am going to cover. So all these are going to be covered on today class. Now let's move on to the basics of root locus. Here, sim, what is mean by root locus? First of all, the root locus is nothing but what? Roots of the characteristic equation. Means locus of the roots of the characteristic equation by varying the parameter, that is k, from 0 to infinity. K value or parameter varies from 0 to infinity. See here the definition of root locus. The root locus is the locus of the roots of the characteristic equation by varying system gain k from 0 to infinity. But we know that open loop closed loop control system characteristic equation. See here characteristic equation from the closed loop control system is 1 plus g of s into h of s, that is equals to 0. So here how to get that characteristic equation from closed loop control system? In previous classes we learn. Here just simply it is R of s is my input signal and here g of s is gain and c of s is output, and some part of the output is returned back to the input, that is through the feedback element h of s. This is the closed loop control system. From this closed loop control system we are going to get the characteristic equation, that is nothing but the transfer function. Denominator part is characteristic equation. Simply here transfer function is nothing but what? Output by input, c of s divided by r of s, that is equals to what? G of s divided by 1 plus g of s and h of s. Here this is denominator term and this numerator term. Denominator term equating to 0, then we call it as the characteristic equation of the closed loop control system. So this is the characteristic equation. See 1 plus g of s into h of s, that is equals to 0. So here g of s and h of s as numerator coefficient and denominator coefficients here, where k is the for representation of g of s and h of s loop transfer function. G of s, that is multiply with h of s equals to k numerator part divided by denominator part. Okay, numerator part divided by denominator part. Here 1 plus g s and h s or g of s into h of s, that is the representation of g of s h of s equals to numerator part to denominator part, loop transfer function. Okay, here transfer function is this, where k is nothing but the multiplying factor or else constant. Here n of s is represent the numerator term or else nth order polynomial of s, numerator coefficient or else numerator part of the nth order polynomial equation, and denominator polynomial d of s is the denominator mth order polynomial equation of in terms of s. Numerator term, denominator term, that is nothing but the transfer function. Here k is the multiplying factor or else here transfer function are where g h of s equals to 1 unity feedback, then g of s equals to k g of s equals to k n of s divided by d of s. This is the transfer function also. Okay, from this system we are going to calculate the root locus. Okay, so these are the basics of root locus. Next, some angle calculation or magnitude calculation or conditions in root locus. Just consider the characteristic equation, that is 1 plus g of s h of s equals to 0. Here g of s into h of s, that is equals to minus 1. So this minus 1 term here, right side minus 1 plus j naught. J multiply with 0 is nothing but what? 0 only. So minus 1 only we will get. See here, for angle condition, magnitude condition, the points on the root locus branches satisfy the angle condition. So the angle condition is used to know whether the point exit on root locus branch or not. So angle condition is used to give the information about the point on the root locus or not. Angle condition. And also we can find the value of k parameter, the points on the root locus branches, by using magnitude conditions also. So we can use the magnitude condition for the points, and this satisfy the angle conditions also. Right here, magnitude condition and phase condition, or magnitude formula as phase formula. Characteristic equation. From this characteristic equation here, real part is nothing but minus 1, and imaginary part is nothing but plus j naught imaginary. So real and imaginary is there. So angle of g of s and h of s equals to what? So tan inverse of imaginary part divided by real part. So here imaginary part is nothing but 0. Real part is nothing but minus 1. 0 by minus 1. So here observe 0 by minus 1. That is 0 by something. Tan inverse of tan 180. So tan inverse get cancelled. So 180 degrees we got. 2n plus 1 multiply with the 5. So angle condition or phase condition, phase angle of transfer function is 180 degrees. See here, the angle condition is the point at which the angle of the open loop transfer function is, and add multiple of 180 degrees. Multiple of 180 degrees here. Okay, see, phase angle calculation formula, this one is important. And coming to the magnitude, here transfer function g of s, h of s, right? So this is the loop or open loop transfer function. So open loop transfer function is g of s and h of s. Here also open loop transfer function, g of s, transfer function. So numerator by denominator, k is constant. Okay, this is the loop, open loop transfer function. Here also characteristic equation from that open loop transfer function, numerator part or real part and imaginary part, consider that, calculate the angle of that characteristic equation or angle of that system, and also magnitude of that system or open loop control system, g of s, h of s modulus of, here g of s and h of s modulus, that is the magnitude value, that is equals to real part square plus imaginary part whole square. Real part whole square plus imaginary part whole square. Real part is nothing but what? Minus 1 whole square. Imaginary part is 0, 0 square. So you will get the 1. So magnitude is 1 and phase angle is 180 degrees. The magnitude condition is that the point which satisfies the angle condition at which the magnitude of the open loop transfer function is 1. When it is satisfied the angle condition, so angle 180 degrees satisfied at the magnitude equals to 1. So you can remember this one. Okay, next coming to the importance of root locus. Importance of root locus. Why we are going to use root locus here? So root locus technique is an important tool in designing control system. See here, root locus technique is an important tool in designing control system with desired performance characteristics. Desired performance characteristics. Why we are going to use the root locus in control system means we are going to identify or else locate the poles or roots of the higher order polynomial equation. Any higher order polynomial equation, we are going to locate the poles on the S plane. So easy to locate the poles by using the root locus technique only. So that's why it is the very useful to determine the roots of the given control system or given any system. Roots or poles location. Okay, see here, the desired performance of the system can be achieved by adjusting the location of its closed loop poles in S plane by varying one or more system parameters. Okay, by varying the system parameters, we are going to locate the or adjust the poles on S plane to get the desired performance of the system. And here the root locus can be plotted in S plane by varying a system parameter, that is gain k, over the complete range of values. K value is up to what? 0 to infinity. Any values, any range of 0 to infinity between values are going to be vary, and we are going to plot the root locus on the S plane by varying the parameter k, the total ranges or complete range values of parameter or gain k. So the roots corresponding to a particular value of the system parameter can then be located on the locus, or the value of the parameter for desired root location can be roots location can be determined from the locus. From the root locus, we are going to determine the location of the roots or poles and the root locus on the S plane. So by that we are going to consider the or vary the parameter or system parameter or gain value, that is k equals to 0 to infinity. And also the root locus technique is very useful for stability analysis condition also. The system is stable or unstable condition. For that, for higher order systems or higher order polynomial equations, the root locus technique is very useful. See, the root locus technique is also used for the stability analysis for higher order systems or higher order characteristic equations. Okay, for in previous session we learned RH criterion method. Some of the S power of 7 or 8 or 10 up to, for example, S power of 20, S power of 9, 10 above, like 11 or 12 or 13, like that. Powers are there, more highest powers are there. So it is difficult to calculate the poles or roots location by using the RH criterion method. So that's why we are going to overcome that problem to use the root locus technique on that. So by using root locus technique, we are going to estimate the or locate the poles on the S plane for any higher order polynomial equations. That is a very important for using of root locus in stability analysis for a stable condition. So here see, some of the rules are available for construction of any root locus. For some of the rules I am going to explain now. See, rules for the construction of root locus. The root locus generally, it is a graphical representation, and also it is in S domain, and it is also in symmetrical. Root locus is always symmetrical about the real axis. See here, you know, imaginary axis and real axis. This is what real axis, this is what imaginary axis. So here the root locus is always symmetrical about real axis. So this is the real axis. So real axis, the root locus is always on this real axis only, means it is a symmetrical about the real axis, because the open loop poles and zeros exist on the S domain, having the values either real or as complex conjugate values. So here see, the root locus is a graphical representation in S domain and it is symmetrical about the real axis, right? Because the open loop poles and zeros exist in the S domain having the values either as real or a complex conjugate pairs. In this chapter, let discuss in this root locus concept, or in this chapter, just we are going to construct or draw the root locus by applying the some rules. So by applying some rules or follow the some rules to design or draw the root locus. The first rule here, we are going to locate the open loop poles and zeros on the S plane. For example, this one S plane I consider. So locate the open loop poles and zeros. Poles representation, here poles representation small cross mark and zeros representation small circle. So if poles three poles are present on the left of the S plane, for example, here I am going to draw the one pole and here one pole and here one pole. Cross mark is nothing but the pole representation, or zero mark is represent, or small circle representation the zeros. So locate the poles and zeros. Simple. Like that we are going to locate the poles and zeros from the given open loop or control system, open loop system. For example, g of s k divided by s into s plus 1 s plus 2. For example, here s equals to 0 1, s equals to minus 1, s equals to minus 2. Denominator part equals to 0, you will get the roots here. So all three poles, so three poles are present. Here s equals to some one pole present is there, s plus 1. So sorry, 0 is present, s plus 1. So or s minus 1, s plus 1, or else here this one is 5, for example, s plus 5. So here this one is the representation, minus 0, minus 1, minus 2 and so on 5 up to. Like that we are going to represent. Look at the open loop poles and zeros in the S plane. And second point or second rule, find the number of root locus branches. Number of root locus branches. Here simply n is nothing but the total number of the open loop poles branches. So here we know that for example I am going to consider the n is nothing but the branches. Here we know that the root locus branches start at the open loop poles and end at the open loop zeros. See one thing, observe. This is pole representation, right? Root locus starting point at a pole only, ending point at a 0 or else end at the 0 or else infinity. 0 or else infinity. So here, so the number of root locus branches in number of root locus branches, this one equal to the number of finite open loop poles P or the number of finite open loop zeros Z, whichever is greater. For example, mathematically we can write the number of root locus branches n is, for example, number of root locus branches n equals to P. When the poles are equals to the number of locus branches, root locus branches, when it is comes, if the poles are greater than or equals to zeros, if the poles are less than zeros, the zeros are nothing but the number of zeros are nothing but the number of root locus branches. Simply, how to find the number of root locus branches? First you should how many poles are present from the given question and how many zeros are present. If the poles are greater than or equals to zeros, then the number of root locus branches are nothing but the number of poles. If the number of poles are less than zeros, the number of root locus branches are nothing but the number of zeros. Simply we are going to consider this. Next, coming to the third rule, root locus on the real axis. To find the root locus on real axis. Here real axis, imaginary axis and real axis. This is the real axis and this one is the imaginary axis. So we need to find the root locus on real axis. Always root locus symmetrical about real axis, right? So root locus on the real axis. So for that we are going to choose one test point. Okay, on the real axis, but it must be available on the root locus only. So here, in order to determine the part of root locus on real axis, take a test point on real axis and choose the test point on real axis. After that, count the number of poles and the number of zeros of right side of the test point is odd number. Then the test point lies on the root locus only. If it is even number, then the test point does not lies on the root locus. Two things, very important. How to identify root locus on real axis? Take the test point and after test point right side, how many poles and zeros are available? Just to count. If it is equals to odd number, then root locus, then test point is available on the root locus. So in there exists the one valid root locus is existed on that place. If it is even number, there is a no valid root locus. So there is a root locus is not available. So simply we say that. Okay, for that test point going to be considered. For example, here see, here I am going to draw one cross mark, that is nothing but one pole present at origin, next pole -1, next pole -2. Now in between 0 and -1 is there any root locus, or between -2 -1 is there any root locus, after -2 is there any root locus? Just we are going to choose root locus on real axis. How to measure? So see, first from here to here I am going to first take the test point between these two. So after test point right side, just count how many poles and zeros. Here one pole is there, so one pole, so odd number. So there between the -1 and 0 the root locus is existed, but root locus always start at a pole and end at a 0 or infinity. Okay, next I am going to consider test point here. For example, test point, after that here one root locus, valid root locus is occur. Test point after how many poles? 1 and 2, 2 poles, so even number, so this one, so even number, so that's why it is between these two, -2 -1, there is a no valid root locus is existed. After that here I am going to choose the test point here. This is test point. So test point, after test point how many poles? 1 2 3, so 3 poles are there. So it is also valid root locus between after -2 to -infinity, because of pole root locus is started the pole and ended the infinity, or else the 0. Okay, these two are the root locus. Like that we are going to find the root locus or draw the root locus on real axis. Okay, next angle of asymptotes and centroid. Angle of asymptotes and centroid. Here odd number means root locus is existed. Right side only, you must count the right side of the test point only. For example, right here test point right side 1 2, so 2 are even number, no valid root locus here in place. So this one root locus, here root locus, 2 root locus spots. Angle of asymptotes and centroid. So angle of asymptotes and centroid. From centroid, the asymptotic lines are passing from the centroid only. So here these two are the important formulas. Just the same. If n is number of poles and m is number of zeros, or else p is poles, z is zeros, then p minus z or n minus m root locus branches will terminate at zeros at infinity. These n minus m root locus branches will go along an asymptotic path and meets the asymptotes at infinity place. Hence, the number of asymptotes is equal to the number of root locus branches going to infinity. The angle of asymptotes and centroid are given by the following formulas. Just simply, you are going to remember these two formulas. For example, for angle of asymptotes formula, see here, angle of asymptotes is equals to plus or minus 180 degrees multiply with 2q plus 1 divided by n minus m or p minus m poles minus zeros. So this is the calculation of angle of asymptotes. Asymptotic lines are passing through the centroid only always. Okay, must remember. And number of poles minus number of zeros, that is nothing but the root locus branches. Root locus branches, poles minus zeros, that root locus branches are going to be terminate. How many root locus or branches are there? So for example, here q equals to 0, 1, 2, 3, so on, n minus 1, n minus m. For example, here 1, 2, 3, 3 poles, right? So poles equals to 3. So 3 minus 0, 0 zeros, 3. So 3. How many asymptotes lines are there? 3. So up to, so 3 minus 0 is 3, up to 3. So q equals to 0, 1, 2, 3. So number 3 up to 3. So total 0, 1, 2, 3, 4. Right. So for example, p equals to 3, z equals to 2, p or n, z equals to 2. 3 minus 2, what is the value? 1. 1 up to 0 and 1, number 1. So here in this condition 3 poles, for example 3 poles, 3 minus 0, so 3 up to 3. So 0, 1, 2, 3, 4 asymptotic lines. These are the asymptotic lines to find angle of asymptotes. Next, centroid. Centroid is the meeting point. Asymptotic lines just meeting one point. That point is nothing but the centroid, simply. That centroid point on the real axis. See here, meeting point of asymptote with the real axis is nothing but the centroid. Centroid formula also very important. Here, sum of the poles minus sum of the zeros divided by poles minus number of poles minus number of zeros. For example, here 1, 2, 3, 4, 3 poles are there. One, I am going to one consider as, so okay, 3 poles are present. So minus 1, minus 2, for example here 0. So 0 plus minus 1 plus minus 2. This is the sum of the poles minus sum of the zeros, there is no zeros. So 0 divided by number of poles 3. Number of poles is 3 and zeros is 0. So minus 1 plus minus 2. Minus 3 divided by 3. Minus 1 is the centroid. So simply we are going to calculate like this. See here. Minus 1, or otherwise I am going to write here sum of the poles. Sum of the poles here how many? Minus 1, 1 pole, 0, 1 pole, minus 2, 1 pole, minus sum of the zeros is 0 divided by number of poles is 3, number of zeros is 0. So minus 3 by plus 3, that is equals 3 divided by 3 minus 1. Minus 1 is our centroid. For example, poles are 3 available. Zeros are not available in that condition. This is the calculation or find the angle of asymptotes and centroid, root locus on real axis, and also how many root locus branches are available and how to locate the poles and zeros on S plane. All these are the rules for the construction of root locus. Next, some of the rules are available again. So I am going to explain all the remaining rules for the construction of root locus for the next coming classes. Okay, so I hope you understand this my how to follow the rules to draw the root locus and some of the rules here, and also what is the importance of root locus for higher order polynomial equations. For poles or roots are going to be located on S plane is easy by using the root locus technique, and also stability analysis for the any system. For that the root locus is very useful, and also magnitude calculation and phase calculation from the characteristic equation. These are the formulas also very important, and also basic of root locus means here what is meant by root locus. The root locus nothing but the locus of the roots of characteristic equation, and by varying the gain k from 0 to infinity. So that is the root locus. This is about the basics of root locus and importance of root locus, and also some of the rules of construction of root locus. All these are about the root locus technique only. So coming to the next class, we are going to see the remaining rules. I hope you understand my all the points. This is the very important for you. Thank you all.